thing as the other one. Yeah. F times G could be written as F times G of X, or F of X times G of X. They all mean the same thing. Multiply your two functions together. So I'm going to have X squared times 1 over X plus 1. And just because it's easier than the addition and the subtraction, I'm actually going to multiply them together. Because I can just throw that over 1, multiply the tops, and multiply the bottoms. So this comes out to X squared times 1 is X squared. 1 times X plus 1 is X plus 1. Just because the simplification was easy, we might as well do it. What's the domain of this function? The same. All x's except -1. All right, and then f divided by g. Okay, we could write this as just f over g, or f over g evaluated at x, or f of x over g of x. They all mean just take x squared and divide by 1 over x plus 1. Now what's the domain of that guy? Before we simplify it, I'd like to find the domain. Any values of x that you want to avoid plugging into that? Still not -1, right? Because I have this fraction here, 1 over x plus 1. Don't want a 0 in the denominator. So my domain is still all x's such that x does not equal -1. Also, this whole fraction, 1 over x plus 1, whatever the function g is that you're dividing by, you have to make sure that that whole function is never 0. Because this 1 over x plus 1 is a denominator of itself. So I don't want it to ever be 0. But what could it be? 1 over x plus 1, can that ever equal 0? Let's check it out. Can 1 over x plus 1 equal 0? Is there an x value that would make that true? Why not? Can you explain? Right. You just can't. Why? Right. Because 1 over something could never be 0, right? So the only way a fraction can equal 0 is if its numerator is 0, right? No matter what this denominator is, even if the denominator is 0, then it's undefined, right? But no, so no matter what the denominator is, this is going to be a fraction, some small amount. So this is never true. You can never make that fraction equal to 0. But it is something that you need to check in general. When you're doing a division, make sure that g of x isn't 0. So you have one extra restriction when you do the division. So your domain for addition, subtraction, multiplication, division will always be the same for all of them. But with division, you have the one additional restriction that g of x can't be 0 because you just put it in a denominator. We just lucked out in this one that our fraction could never be 0 anyway. Our g of x could never be 0. And then we could simplify this too, right? We could rewrite this as x squared, and instead of dividing by this fraction, multiply by its reciprocal. And we end up with x cubed plus x squared, which looks like it has no restrictions, right? Which is why I had you do the domain first. Because we know that there are restrictions because g is technically in the denominator. All right, so before we do that, I want to do one more example, maybe with square roots. So if we let f of x be the square root of x and g of x be the square root of 2 minus x. Let's say I add them together, f plus g. That would be square root x plus the square root of 2 minus x. Can't simplify it. That's just the answer. But then the question is, what's the domain? So I have to be able to plug x into here and into here. So it's the overlap of the two domains of each individual function. So what I like to do is find the domains separately, graph them, and then you can visually pick out the overlap. So what's the domain of square root x? What values of x can I plug in? All real numbers? There's no restrictions? Can't be negative. Yeah. No, negative numbers are also real. That's a good question. Yeah. When you say all real numbers, you mean every number in the world that we know about so far. This would be, you would say this is all positive reals. All right, and then how about the domain of the square root of 2 minus x? What values of x can I put in there? Say that again? Nothing above 2. 2 is the biggest number I can put in. 2 is the biggest number you can put in, because then you'd have 2 minus 2, which is 0. Anything bigger would make the thing under the square root be negative. All right, so if I graph each of these on a number line, so my square root x domain, I'll do in one color. That's 0 to infinity, including the 0. And then my domain of the square root of 2 minus x, I'll do that in another color, and that's negative infinity to 2, including the 2. So this is the domain of square root 2 minus x. The green one is the domain of square root x. I can only pick x's if I'm going to combine these two into a sum. I can only choose x's that can go into one and the other, right? They have to be part of the domain of both. So where do these two domains overlap? 0 to 2. This is going to be the domain of f plus g, or f minus g, or f times g. Okay, so you have to choose x's that can go into both functions. So visually, that means the overlap of the two domains. Any questions on that? Let me just adjust. What if I wanted to find the domain of f over g in this particular example. Right? So f over g would be square root x over the square root of 2 minus x. So the domain when I combine two functions would be the overlap, so 0 to 2. But then what do I have to take out when I do the division? The 2, because I can't let the denominator be 0. So the domain of f over g is going to be 0 to 2, not including the 2. So I have one small adjustment when I do the division domain. Okay, so we've got 4 ways to combine so far: add, subtract, multiply, divide. There is one more, a 5th way that we can combine functions. So that is, we're going to use the outputs of one function as the inputs of the other. You can think of it as putting 2 machines back to back. So you feed your input into one, you turn the crank, it gives you something as an output, then you just pick that up and drop it into the next machine, turn the crank, and get another output. So that's what it would be to compose 2 functions. So we're going to look at some simple parent functions here. Literally parent, different from when I use parent function to mean like x squared and x cubed and absolute value. So here the mother function is going to be m of p, tells you the mother of person p. And the father function is f of p, it tells you the father of person p. So think of this as like a database, right? You type in someone's name or social security number or DNA or whatever, type it in, hit enter, and up pops the person's mother. Right? And then there's another database where you type in the name and up pops the person's father. So obviously, we're going to have to assume that each mother and father is unique. We'll have to ignore the many complexities of parenthood. Otherwise, it wouldn't be a function. All right, so what do you think it means, m of f of p? What do you think that means? No. It is, Megan. Good. It's the mother of the father of person P. So f of P is the father of person P, and then you take the mother of that person. So we have the mother of the father of person P. That would be the paternal grandmother of person P. So paternal grandmother just means grandmother on the father's side. So we have an input, we typed in, right, person P's name. The database told us the father of person P, then we typed that into our other database and got the mother of the father of person P. All right, so now we're going to do a little bit with the algebraic properties of composing 2 functions. So the symbol we use to compose is that little circle, the little open circle. So a lot of people, when they first see this, confuse it with the dot for multiplication, but it means something different. It means compose. Okay. So f composed with g of 3 just means f of g of 3. This means use 3 as your input, feed it into the G machine first, then take your output and put it into the F machine. So you work your way from the inside out. So I'm going to draw a picture of it. of my two successive machines. My G machine is going to come first because that's the innermost function, and then F comes next. So 3 is my input. I'm going to feed it into the G machine. Okay. And then what do you get when you drop a 3 into the G machine in this example? 1/4. Yeah, so G does 1 over x plus 1. So I get 1/4 as my output. Then I take that output from G, drop that into the F machine. And F is the machine that squares things. So what do you get when you square 1/4? 1/16. So F of G of 3 is 1/16. So that is what you do if you do it pictorially. If you want to do it all algebraically, you start innermost first and you say, okay, well, I'm going to figure out what G of 3 is. And you would say, well, that's 1/4. So you replace the G of 3 with a 1/4. And then you apply rule F to the 1/4 and you get 1/16. So if I want to find a general expression for F composed with G of X, that means F of G of X. Again, I'm going to run my two machines in succession. G comes first, then F. You work your way inside out. So I'm going to draw my pictures. Okay, so I've got G and then F. And I'm going to drop in a random input. Instead of a specific number, I'm going to drop in an X this time. So what do I get when I drop an X into the G machine? What does G do to it? 1 over x plus 1. Yeah. That's what comes out. 1 over x plus 1. Okay, so then I'm going to take that output and drop it into the F machine. And F is the machine that squares things. So if I'm putting in 1 over x plus 1, what comes out after it goes through F? The whole thing squared. So that's my formula for F of G of X, for F composed with G. If I wanted to do it all algebraically instead of drawing two machines, I would start with F of G of X, and I would replace G of X with its formula. So before I replaced G of 3 with a number, now replace G of X with its formula. So this says now F of 1 over x plus 1. Just make that substitution. And then F squares stuff. So this is 1 over x plus 1 squared. So you can do it either way, whatever makes sense in your brain. When you do the domain of a composition, here's where the pictures can be really, really helpful. So draw them for as long as you need to. Don't hesitate to draw two machines next to each other, especially when you're finding domain. So let's go ahead and draw my two successive machines for F composed with G. G comes first, then F. X goes in here. Out comes 1 over x plus 1. We put that into F. We get 1 over x plus 1 squared. This is just a picture of our composition. Same picture we just drew. This is how we calculate F composed with G. Now we have to make sure, if we're going to find the domain, we have two function machines, and we have to make sure that neither one jams. Okay? We're in charge of making sure that both machines always run smoothly. So when I look at function machine G, are there any x's that I want to not put into the function machine G? -1, right? Because g does 1 over that thing plus 1. If I put in a -1, I'm going to divide by 0, and my machine screeches to a halt, right? So this machine, make sure x is not -1. How about in my F machine? Is there anything I want to avoid putting in the machine that squares stuff? Why not? This is the machine that squares stuff, right? Is there any number that you're not allowed to square? Nope, you can square anything. Right. So if I put a -1 in, I would jam the G machine and it would actually never get to F. So I've already established don't start with -1. It's already a restriction. But there are no numbers that I have to avoid squaring, right? I can square anything. So the F machine has no restrictions. So I can put in whatever I want. Whatever comes out of G can go into F, no problem. If it went through G, fine, then the output will go through F just fine. So I only have one restriction, -1. I get -infinity to -1, union -1 to infinity is my domain. So it seems like it's the same domain as all the other ones, right? But it's not always the case. So we're going to do one more. Actually, you're going to do one more in your groups. I gave you a new function, h and k. I want you to go through and do a and b, and then we'll do c together. Okay. So h composed with k of 9 means h of k of 9. Take that 9 as the input, it goes into k first and then into h. So if I do it algebraically, I evaluate k of 9 first. Okay, work from the inside out. What is k of 9? 3, because k is the square root function, so k of 9 is 3. So I replace the k of 9 with a 3, and then I evaluate h of 3. And what is h of 3? 1 over -1, which is -1. So I'm going to find a general expression, h of k of x. X goes into the k function first. So what is the formula for k of x? Square root of x. So I'm going to replace k of x with its formula. And then I take square root of x, and I'm going to plug that into the h machine. So what am I going to get? Right. In the h formula, we replace the x with the square root of x. All right, so if I want to find the domain of the general expression that I just found, so notice I didn't draw the pictures for the first two. You totally can. But I wanted to show that it's relatively easy to do these two without the pictures. This last one, really helpful to draw the pictures. So I'm going to draw them now. When I do h of k of x, that's two machines, k first, and then h. When I put an x into the k machine, out comes square root x. K is the square root function. And then I take that square root x and I put it into h, and out comes 1 over the square root of x minus 4. Now, Does K have any restrictions on the values of X that I can put into that machine? You can't square root a negative, so I can only put in 0 to infinity. I can only put in positive numbers or 0. Now, what about the H machine? Do I have to worry about any values in going into the H machine? 16 cannot go into the H machine. Why not? Right, I'd get a 0 in this denominator. The square root of 16 is -4. Yep. But so 16 can't go into H, which means that what do I have? I only have control over what goes into what X I put into the first machine. So if I want to keep a 16 from going into H, is that right? Hold on, let me think about it for a second. Yeah, I want to keep from putting a 16 into the H machine. So what X should I not put into K? Yeah, 16. I shouldn't put a 16 in here. So this machine don't let X equal 16. So I can only put positive numbers, but not 16. I can put any positive number, 0 to infinity, but I have to leave out 16, because if I put 16 into my succession of machines, right, I put a 16 into K, out comes 4. Okay so far, right? It didn't jam the K machine, but if I try to take that 4 and put it into H, did I write down the function right? Yeah, I did. Okay. If I try to take that 4 and put it into H, what do I get as an output? 1 over 2 minus 4, which is -1/2. So 16 actually seems fine. Neither machine jammed. Yeah. Yeah. So let's see. If I put in a 256 here into the K machine, when I square root it, what do I get? 16. Then I try to take that 16 and drop it into H, and I end up with 1 over 0. I end up with a broken machine. So it's not 16 that I have to be wary of. It's 256. You're right. Yeah, you're right. You're absolutely right. Thank you. Yeah. Good catch. So I don't let X equal 16. So it's very tempting if you just go back to the beginning and look at your two functions. It's easy to say X can't be 4 and X has to be positive. Right? It's tempting to just look at the domain of the two functions separately. But it's actually not X equals 4 that we have to worry about. Because I can put 4 in, right? If I take my function machine and I put in a 4 into K, K square roots it, and out comes a 2. Then I take that 2 and put it into H, and I get 1 over 2 minus 4, which is -1/2. Fine, I didn't jam either machine. Okay, so 4 is not the problem, 16 is the problem. So my final domain ends up being 0 to 16, union 16 to infinity. All positive numbers except 16 will be okay in that machine. Does that make sense? Sorry, I messed it up. All right, so I'm going to have you jump over this worksheet for a minute because I want you to try just do 1, A, and D. Okay, so practice finding a formula, evaluating, and finding a domain when you're adding and when you're composing. Okay, so for F plus G, I would just do, for me, it makes sense to do the formula first and then plug 2 into it. Some people like to plug 2 into each function separately and then add them together. Comes out the same. So whatever you like to do better. I'm going to do the formula first, then plug in 2. So F plus G, that would be square root x plus 2x minus 1. So that means that F plus G evaluated at 2 would be the square root of 2 plus 3. You could put that in your calculator and get a decimal, or you could just leave it like that. Doesn't matter. So here's my formula. Here's my function evaluated at the point x equals 2. And then for the domain, graph both of them, the domains of both, and take the overlap. Okay, so what's my domain of square root x? Come on, I know you know what it is. What functions can go into this? I mean, what x values can go into the square root function? 0 or greater. So if I graph the domain of the square root function, it looks like this. And what values of x can go into the function 2x minus 1? Anything. I have no restrictions on that one. So its domain looks like this. So where do the two domains overlap? 0 to infinity. You don't always have to draw the pictures for a simple example like this one, but very often they can get complicated quickly, and the graphing the domains can really help. So my domain of f plus g is 0 to infinity. The overlap of the domain of f and the domain of g. All right, so let's look at f composed with g. This one, maybe I'll plug the 2 in first. F composed with g of 2. So first thing I do is I work from the inside out and I try to evaluate g of 2. What is g of 2? 3. So I replace g of 2 with a 3. And then f is the square root function. So my f of 3 is going to be square root 3. My output of the composition. Does that make sense? Okay, so when I do the machine, when I do the two machines in a row, when I plug in an x, I get f of g of x replace g of x with its formula, which is 2x minus 1. Apply the rule f to the function 2x minus 1, and f square roots things, so this is the square root of 2x minus 1. And if I want the domain of this thing, I draw my two function machines. G comes first, then f, because you work inside out. First I put in an x, and g is going to do 2x minus 1. I plug that into f, take the square root of the input, so that's my new output. Do I have any restrictions on g, the function that multiplies by 2 and subtracts 1? No, no restrictions. Now f is the square root function. Does the square root function have any restrictions? Yeah. What is true about the square root function? What are its restrictions? Can't square root a negative number. 0 to infinity are the values I'm allowed to put in for f. But the things going into f are 2x minus 1s. I have to make sure that the 2x minus 1s that are coming out of g are always positive or 0. So if I solve this thing for x, I get x has to be bigger than or equal to 1/2. So if I want to keep the things going into f positive, I have to manipulate what goes into g appropriately. I can't control what goes into f directly as the manager of this machine shop. I have to plan ahead and say, okay, if I don't want to jam f, I have to think about what x's I can put into g. I can only put x's in that are bigger than or equal to 1/2. So let's see what happens if I try to put in, say, 0. If I put a 0 into the g machine, I'm going to get -1 as the output. Then I take that -1 and I try to put it into f. When I square root the -1, can't do that. I broke the g machine, the f machine. So g has no restrictions, which means I have to think ahead about what to put into g to make sure I don't break the f machine. So I can only put in x is bigger than or equal to 1/2, or 1/2 to infinity in interval notation. Does that make sense? Okay. All right, so now I want you to go back and work in your groups on this worksheet, composition of functions. So this is a real life kind of thing. I just want to point out the labels are in kind of weird places. So this T of D label should be the title of this graph. This is T. This is the T graph. And then this F of T is the title of this graph. This is graph F. Okay. F of T, T of D. So the variable letters are the first, it's the first letter of the thing it represents. So D represents distance, T represents time, and F represents fuel usage.